And welcome to Subnetting 4 of 4.
This is going to be an exciting lesson because we're going to give you some shortcuts on how to do subnetting. We're going to go ahead and review our learning objectives. Why we want to learn about shortcuts for subnetting. We're going to do some exercises as well as a learning verification, and as always, we will summarize at the end of this lesson.
Okay, so after we go through the lesson today, we'll understand these learning objectives. What subnet mask matches a /28? What subnet mask matches a /29? What is the block size for a /27? What is the block size for a /23? How does the subnet matter when sending traffic to a destination in the same subnet? How does the subnet matter when sending traffic to a destination in a different subnet? What is proxy ARP? And what website can we be used to practice subnetting? Now, why would you need subnetting shortcuts? Okay, first, a big disclaimer. Maybe these are some good shortcuts and maybe they're not. It is hoped that the prior lessons established the mathematical basis in binary and subnetting to realize that what is covered in this lesson is not really shortcuts as much as they're an extension of the underlying knowledge. Warning! Warning! If you do not have knowledge from all prior classes, then this presentation may be confusing for you. The prior classes have been binary, hexadecimal, Ethernet, IPv4, ARP, ICMP, and subnetting 1, subnetting 2, subnetting 3. So you have not had those prior classes or the knowledge you've gained from them. Also now, you may need a shortcut as a quick sanity check. For example, you're taking a timed certification exam and you may not have time to work out those long problems. Also, addressing is important enough to take any required extra time to verify that the subnetting is correct. Basically, I'm trying to balance out the sometimes need for shortcuts versus the reality of not often should you need to use a shortcut for subnetting. You know, if you're going to do it right, there won't be any shortcuts. Now, also, what's important is knowing what happens if a subnets are misconfigured. You don't want me to talk about proxy ARP again, do you? Now, because I talk about it a lot. I guess it's one of my pet subjects, I'm not sure. Now, once you get beyond subnetting, you'll be able to experience the joys of networking. AKA, by now, you should have grilled into your head that whether or not hosts think they're in the same subnet is a pretty important thing for networking. Okay, exercise number 1 of 10, looking for patterns. And now we have here several IP addresses that all are using the same subnet mask. And it actually tells us here to define the network address given an IP address in mask, and it wants us to show our work. As you see, we have these IP addresses all with the same subnet mask, and we need to find the corresponding network address for each of these IP addresses. Now, here we take this decimal and we translate it to binary. We take this decimal, translate to binary. We did this across all these IP addresses and subnet masks. Then, as you recall, to obtain that network address, we had to use binary ANDing to translate these to a network address. We had to binary AND the IP address and the subnet mask to obtain the network address. This is how you do it. And so we did that for all of these, and then we obtained what network address correspond to these IP addresses. We did it as so. Now, as noted here, we use binary ANDing to realize the network address. There was a prior subnetting video number 2 for specifics on how this works. So go back and review the prior subnetting videos 1 and 2 if you're not clear on what binary ANDing is. Exercise 2 of 10, looking for patterns. Now, what is an octet and what subnet mask matches the /28? We covered this previously. An octet is a group of 8 bits. As stated here, it should have been covered earlier. Now, in a subnet mask that matches a /28 is 255.255.255.240, which you should be familiar with from doing our decimal to binary translations, and also from our prior work with the CIDR table. As you remember, we worked with a VLSM table. Exercise 3 of 10. We're still looking for patterns here. Now, what possible network addresses could appear in the 4th octet if the subnet mask is a /28? And for purposes of this exercise, we are ignoring the first 3 octets. And I will explain why we're ignoring them later. Answer on the next slide. Now, here we're only looking at the 4th octet here. Now, we're wondering what are the possible network addresses. So to look at all the possible network addresses that could appear, we're going to look at these bits right here in this 4th octet. And an octet means 8 bits, right? So we're looking at these 8 bits, and we can see the subnet mask overlaps these 4 bits. So we're going to see what's all the different possible patterns we could place here, and then what that would translate to with regards to a network address. So we could say, okay, we'll use all zeros. Okay, then we'll just turn on this bit. Okay, so we actually went down, all the way down, and we just turned on these bits incrementally. As you can see, we tried out all the different combinations, starting from the lowest up to the highest, even continuing on to the next slide. But you should actually notice some sort of pattern here until it got to the point where all the bits were turned on. And this will reveal to you all the possible network addresses that could appear in this octet if you use this particular subnet mask. Exercise 4 of 10, looking for patterns still. Because if we can't spot these patterns, we won't be able to take advantage of these shortcuts. Now, when evaluating a /28 mask, why can the first 3 octets be ignored? Please note they were ignored. Review the prior question and see if a pattern is noticed yet. So we'll look at the prior question right quick. Do you see any sort of pattern here among these numbers? Do you see any pattern at all? Okay, now, why can the first 3 octets be ignored? Well, since all the bits are turned on in the first 3 octets, ANDing these 3 octets will always match the IP address. Now, we're referring specifically to this /28 address in this example. Now, since all the 1 bits will always match, thus the only part of the subnet mask that won't match everything is only in that 4th octet, where the first 4 bits will match everything. Thus, the first 4 bits in the 4th octet are interesting to us, and in this case, the 4th octet is called the interesting octet. So, the next part of that question was, did you notice a pattern? The pattern that you should have noticed is that the possible values will fluctuate based upon the last bit in the subnet mask. So here, if we look at the 4th octet of the /28, the subnet mask of 255.255.255.240, and I give a bit place hint here of 0, 1, 2, 3, 4, 5, 6, 7, and so on. And you remember that octet looked like this. For that subnet mask looked like 1, 1, 1, then 0, 0, 0, 0. And this was equivalent to 240 right here for this octet. Now, you note this bit is valued at 16 because that is 2 to the 4th power. And if you review the prior exercise, the network addresses actually increment in blocks of 16. Thus, this subnet mask has a block size of 16. So let's go back and look. If you'll note, this actually increments by 16. If you'll notice, increments by 16, increments by 16. So that's what I mean by saying it has a block size of 16. The network addresses increment in blocks of 16. Exercise 5 of 10, block size. Define the block size for the given subnet masks. So we have these provided subnet masks, and we need to know what the block size is for all of these. We're going to see the next slide for answers. Now, as we can see here, given these particular subnet masks, here we're only working with subnet masks that end here. So all these first 3 octets you can basically ignore because they're all ones. But the interesting part is happening here. Now, as you will note, the subnet mask always starts from the left and goes towards the right. So here, we stop it here, and we'll say the block size here is 256, because if you'll note, the last bit that turned on is actually the 8th bit, because remember it starts from 0 and 8, and 2 to the 8th is 256. Here the last bit is here, it's in the 7th spot, and 2 to the 7th power actually equals 128. That's our block size, and so on. You'll see for these, the math just works out so cleanly for us for this to be the block size. According to the last bit in the subnet mask that's turned on, 2 raised to that power, and this one, don't be confused, is in the 0th position, and 2 to the 0 power is 1. Block size of 1 here. Okay, now exercise 6 of 10. Now that we're armed with that knowledge, now we can use the block size as a shortcut. But it only works because you understood what happened previously. So here we're going to define the network addresses for the below, given an IP address and mask, and we're not going to show our work. So you can actually subtract the interesting octet from 256 to get the block size. So in this case, given this IP address, this subnet mask, what is the network address? Likewise, given this IP address and subnet mask, what is the network address? So, because we know about finding this block size, we should be able to do this a lot more quickly now. So, as you can see here, we can subtract the interesting octet from 256 to get the block size, and we say here 256 minus 240 equals 16. So we'll say we'll increment block size of 16, and boom, 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 incremented by 16. And so we'll say, okay, this one falls into, okay, 40 falls between 32 and 40. Okay, so network address will be 32. And this one, 50, falls in here, so the network address will be 48. And that's how you did that so fast, because you realized the block size. Now, exercise 7, using the block size as a shortcut. Define the network address for the below given IP address and mask do not show your work. We're just going to subtract the interesting octet from 256 to get the block size. Here, we have the subnet mask, right? And we're just going to subtract this from this 240 from 256, give us a block size. Oh, great, they're using the same subnet mask. So the block size is going to be the same. The only question is, are these in the same network or not? We don't know, but we will find out. So now, this says, okay, increments to 16, 0, 16, 32, 46. Okay, so 60 falls between 40 and 64, and 70 falls between 64 and 80. So 70 uses 64, and this one uses 48. And there we have the network addresses. And if you're not confident in this result, you can refer to the prior lessons and do these out manually by hand. Do the binary ending, and you should get the same result. On to the next one. Exercise 8 of 10. Interesting octet moves around. In this case, we're going to find the network address without showing our work, and the answer is on the next slide. So now you should be able to realize, okay, so now the interesting octet is here. So this will be the value you will subtract from 256 to then obtain your block size, which you would then increment up. So let's see what happened here. So here we have our answers. And so 10.44.32.40 using this subnet mask. As you can see, the interesting octet has moved to here. So we could actually subtract, okay, 224 from 256, and then we get a block size of 32. So we could go 0, then 32, then 64, for example. In this case, this one would fall within the 32 block. So this one would fall into this network address. Here in this example, we're at 10.44.40.40. The subnet mask is 255.255.128.0. So 256 minus 128 would equal a block size of 128. So then we go 0, 128, and then, okay, then we'd be done. So this one would fall within 10.44.0 as the network, 0, 0 network. This one's a little more interesting, and don't be misled here. This one is 10.44.200.40, and we see the subnet mask here. Okay, so 256 minus 192 equals 64. The block size would be 64, and we're trying to get to this number, so we go 0, then we go 64, then we go 128, then we go 192. I say, okay, we found it. So this one would fit within this network, 10.44.192.0. And as I said before, you can double check these with binary ANDing, and these should be your results, and that will confirm your shortcut works as expected. Exercise 9 of 10. What is proxy ARP? I guess this really is one of my favorite topics. Now, proxy ARP is when a device will answer ARP requests for a host that is attempting to ARP for destinations that are outside its network. Proxy ARP can thus be used to mask a subnetting issue the host has, since the host is not recognizing what is and is not on its network. If proxy ARP is disabled, and we're talking about a misconfigured host, this host will not be able to reach these destinations, and the problem with the host must then be investigated and resolved. Exercise 10 of 10. Why not always use block size? I mean, why not always use block size? It's so onerous to have learned all of that binary stuff if I could just simply subtract from 256 and be on my merry way. I mean, why did I waste all this time? Well, the truth is, there is always a chance that you make a mistake if you attempt to use a shortcut without understanding what's really going on. Also, there's a case when, what if the shortcut is insufficient? How is subtracting from 256 going to help you if you don't know what a /26 is? Or what if you're trying to work with IPv6? Subtraction from 256 has no use at all for you in that case. Also keep in mind, even if your shortcuts fail, you can still learn everything you learned prior with regards to binary, subnetting, hexadecimal to figure out any problem that comes your way. So don't use shortcuts as a crutch, is my advice. Learning verification. What subnet mask matches a /28? What subnet mask matches a /29? What is the block size for a /27? What is the block size for a /23? How does the subnet matter when sending traffic to a destination in the same subnet? How does the subnet matter when sending traffic to a destination in a different subnet? What is proxy ARP? What website can be used to practice subnetting? Okay, so the subnet mask 255.255.255.240 matches a /28. And you should know this by now because you have gone through CIDR and translating binary to decimal and knowing what the prefix length is and how many bits are being turned on. And you should just be well versed in this so that when you see /28, you just instantly know what the subnet mask is. And the same should go for a /29. You should just instantly know what to do and how that works out. And the subnet mask should be a 255.255.255.248 for a /29. Now, the block size for a /27 is 32. Reason being, 32, which is the number of bits you have available in IPv4, minus 27 equals 5. And as we know already, 2 raised to the 5th power is 32. The block size for a /23 is 512 because 32 minus 23 equals 9 and 2 raised to the 9th power equals 512. Pretty easy, right? Now, to reach an IP address in the same subnet, the system uses ARP to resolve the Ethernet address of the destination IP address. To reach an IP address in a different subnet, the system uses ARP to resolve the Ethernet address of the gateway. Proxy ARP is what is used when a device will answer ARP requests for a host that is sent to ARP for destination that are outside its network. Proxy ARP can thus be used to mask a subnetting issue the host has, since the host is not recognizing what is and is not on its network. If proxy ARP is disabled, the host will not be able to reach these destinations, and the problem with the host must then be investigated and resolved. Practice. Try www.subnettingquestions.com. I am not behind the website. I don't sponsor the website. I have not virus checked the website. Be careful. Try at your own risk. But that is a website you could try. Just saying. Okay. That concludes this lesson. I'd really like to thank you.